What's up, my fellow chemistry enjoyers? Today I'll be talking about the Curtius and Hoffman rearrangement. Alright, so when we're starting with the Curtius rearrangement, the main reagent that's used is this acetyl azide. You can see it right here. You'll usually start with some type of acid and then get to the acetyl azide. There's a bunch of different reagents that they use to get to that point, so I didn't want to list them out because you'll see different ones. The Hoffman rearrangement, the main reagent uses a primary carboxylamide, which you can see here. So when you're distinguishing these two rearrangements, you would start by looking at what's the reagent that's used at the beginning. So now we'll get into the mechanisms and their rearrangements. So this is the Curtius rearrangement in blue up here. As you can see here, this is like the N3 drawn out in like its full form from the acetyl azide. And what happens here is you just apply heat to it and it ends up rearranging where N2 leaves and the R group gets attached to the nitrogen and it forms a double bond with the carbon here. So you can see here, this is isocyanate, R group here attached to the nitrogen, and then it should be about here for the carbon, but carbon to O, carbon to O, right? The Curtius rearrangement also has a photochemical process, but it causes multiple products, so it's not really used since just the thermal one is just better, more efficient. All right, so for the Hoffman rearrangement, there's also different reagents that are used. So you'll start with the primary carboxylamide that we got from here, but you use like a metal OR, so R can be like a hydrogen, some other things too. Metal OX, so X represents a type of halogen, and then you apply heat after adding those reagents. All right, so here's the mechanism for it. So you end up using OH minus, which is from the metal OR, and this on the reagents, deprotonating the nitrogen, and then you get to this step, and you just pick up the halogen by coming down here with this arrow, pick up the halogen for the nitrogen. So now the halogen's attached to the nitrogen here. And the way you draw these arrows is first starting with this one to form the double bond, and then showing the rearrangement happen, and then the halogen leaving, which ends up getting you to the isocyanate product that's seen right here. So yeah, like this step would be like the heat step right here. And then the isocyanate also is kind of like you don't isolate it, and a lot of times it'll go to carbonic acid, which is unstable. So people would also add like terbutyl OH or something like that and do a Fischer esterification on this carboxylic acid. Or they'll do, like if there's already like alcohol groups in their like structure, this will end up like cyclizing with the rest of the structure. Like that's kind of like the plan with that process. So yeah, so those are the basics for them. This is a literature example up here. So this is the original structure that they ended up getting at some point in the paper. As you can see up here, here's an acid that we can use to do a rearrangement. So if you want to try to figure out which type of rearrangement it is, pause the video. But DPPA is an example that's used for the Curtius rearrangement. So you add DPPA, and that's how you end up getting the acetyl azide, which you get, and then you apply the heat, right? So then you get this like intermediate, as you can see here, that's the isocyanate on the structure from the carboxylic acid, and then you just do an electrocyclization, like a paracyclic reaction that we learned, and you end up getting this, boom. So yeah, that's really it.